Hi, everybody. I'm Cameron. I basically, for some context of me, my current tech stack here at BBD is React, TypeScript, JavaScript. I did a physics degree at UCT, which is kind of what got me into this sort of thing, quantum computing, and just playing around with it. So when was it? In December, I was lucky enough to go to attend a conference where there was a workshop on machine learning on a quantum computer, so quantum ML. And by attending that, it showed me how easy it is to right now get your hands on an API that will let you go and make quantum programs, which I'll explain in a bit, and get yourself up and running and start playing around with this really interesting cutting edge tech. So to put it out there from the start, there isn't really a practical use case for quantum computers at all right now. And the reason for that is that we have a whole bunch of real world problems that we can run on normal computers. It takes ages to run, but we need to find mappings to recreate those problems on a quantum computer. And finding those mappings is the biggest issue. So today I called it Hello World on a quantum computer, but Hello World doesn't really have a mapping to a quantum computer. So instead, I'm going to give a demo of a problem that has a mapping and is quite intuitive to us. This demo is a heads or tails game. So to start, heads or tails, the only thing we care about is the coin has a 50% chance of being heads, 50% chance of being tails. If it's heads, we win. So let's say with a bit in a binary system, 1, we win, 0, we lose. So it's a fair coin. So it should be every time just random. We can map this to a quantum computer. So the way we can do that is we make a thing called a quantum circuit. And what a quantum circuit is, it's analogous to a normal logic circuit in a sense, where you have a bit, a bunch of logic gates on that bit, and it gets an output. Same thing happens in quantum on a quantum computer, except the gates are quantum operators. So that's where it delves into the physics and the maths behind it. Anyone who's done any form of linear algebra, all quantum operators is a set of matrices or matrices that get applied to the bit. In this case, our bits are called qubits, quantum bits. And what makes them very special is that they can be in 3 states. They can either be 1, 0, or both at the same time. And when they're in the both state, it's called superposition. And so we're going to leverage superposition to get our random number generator, so to speak, our random true coin. So to start this demo, firstly, there's a link on the chat if anyone has their laptop and wants to play around. It's a GitHub link to this code that you can clone. There's a README. Hopefully it still works. One thing I found with this is that the developers are working on this Qiskit, which is the API, this Qiskit API faster than updating the docs. So if you go to IBM's platform, which is who makes Qiskit, and you say, hello world tutorial, it'll be wrong. You can't run that code. It's got errors. This is deprecated, but hopefully this stays up to date for a month or 2. But anyway, so what we're going to do is we're going to initialize all the Qiskit packages that we need already installed. This is Jupyter Notebook, so we run it block by block. We're going to run this coin flip program on the IBM Quantum Compute platform, which IBM give you 10 minutes of compute time for free on a real quantum computer. However, it takes about a day to get your job scheduled to run. So we won't be running on their real computer because it's too slow, but they have simulators, which are really good. They simulate that quantum computing hardware essentially in the best way we can. So we're going to run on that. So in order to do this, you set up an account, you download your token, and you are away. So I talked about quantum circuits. So what this code here does is it initializes the quantum circuit. And I'll show you the quantum circuit it initializes. It looks like this. So the word circuit there is your qubit. It's the qubit. It starts in a base state of 1, I'm pretty sure. And then we apply a gate. The gate is the H. It's called a Hadamard gate. And what that does, at this point in time, before you apply that gate, in that tiny black line beforehand, this one, it's essentially the same thing as a normal bit. Once you apply the gate, it applies a matrix to it, and it puts it into that superposition. So it could be 1 or 0 at any given time. Then after that, you can take a measurement. Take the measurement, it returns 1 or 0. You don't know which, it's non-deterministic. That's some really cool maths if you're interested. But it talks about the wave function. If anyone's done, I think, some mechanics there. But that's not the point. The point is, once you take that measurement, it collapses. The function collapses into that 1 or 0 state, and it doesn't change. You can measure it 1,000 times. It will always be 1 from then on, or 0 from then on. But the cool bit is that Hadamard function, Hadamard operator, that logic gate, essentially, that puts into superposition. So with that, this code just sets up a bit of a UI, and it does a bit of logic. It creates the initial circuit. It puts that measurement in. It then gets the quantum back in. For this case, we're using a simulator. Then it just logs what's going on. It runs the job. So when you run a job on a quantum computer, you submit it. The reason why it's so powerful is you can, when you run a large number of jobs, let's say thousands of jobs, it gains a statistical significance, and that's where the power in real world is. However, for a coin flip game, having statistical significance, all it should show us is that it's 50-50, right? It's either, if I run they call them shots. If I run 1,000 shots, so that's 1,000 repeats, where it creates a circuit, measures the circuit, deletes the circuit, creates the circuit, measures the circuit, deletes it, captures all that information, averages it. So it should be 50-50 for a true coin. But if we take one measurement, it's exactly the same thing as just a random measurement. So that's what shots are. That's how things get run on the quantum computer. Then I just do some logic to say if we lose, who loses, who wins, if we draw, whatever. So down here, we can select the number of shots. I'm going to do 1. And when we click play, it creates a circuit, submits the job ID. It runs, it gives us a result. So the sampler result is what IBM returns. It says quasi distances. All that means is it's a object or a dictionary with the different states that the system, the circuit, can be in. Because I have 1 qubit, I can only ever get 0 or 1 in that object. But if I had multiple qubits, because you can make quantum circuits with many qubits, and that's where it gets really cool. But if I have multiple, I would get combinations of those states. Like if I have 3 qubits, I could get 0, 0, 0. That means all of them are in the 0th state. If I look at 0, 1, 0, that type of thing showing there. I'll show you something like that in a sec. But anyway, but in this case, 0, it returns 0 100% of the time is what that means. Obviously, we did 1 run, so whatever the output was is 100% of your runs because we did 1 shot. And in that case, 0 was tails, so we lost. If I play it again, maybe we win. Let's see. Yeah, you win. Okay, cool. It came out as heads, we win. I can play it as many times as I want. It will repeat. So that's pretty much what we did there, is we mapped a random coin flip, true coin, onto a quantum computer, ran it on a quantum computer. That's all that happened there. To show you the idea of increasing the shots. So if I increase the shots to 10, it will run 10 times. And let's see what the output is. And then, cool. So it came up heads 3 of the times. It came up tails 7 of the times. That's what that is. I can run it 1,000,000 times. It will average out. Obviously, the bigger the number of shots, the more smooth that data will be. So why not? I think sadly the max I got to is 100. You want to do thousands to actually get statistically significant results. But there you go. For example, in 100 runs, 46 of them were tails, heads, 54 were tails. So that's essentially a program running on a quantum computer flipping a coin. So, well, 5 minutes, right? Okay, one thing I want to show you that I think is fascinating, and I'll open up for questions too, but this is a really nice visual representation of building quantum circuits that IBM have. And what I've got here is exactly that circuit that I had beforehand, where I've got my qubit, Hadamard gate, and my measurement. Where quantum gets crazy is a thing called entanglement. I'm not sure, has anyone heard of quantum entanglement before? Awesome. Sweet. So spooky action at a distance, right? That's kind of what that is. So what that means is if I add another qubit, there's another way I can map this problem to, do I add another qubit now? There we go. There's another way I can map this problem to a quantum computer. I can not measure my qubit that I put into superposition. I can measure my other qubit. So as you saw there, wait, hold on. Bottom corner, we get the probability of states over 1,024 shots. I'm not sure if that's easy to read, but there you go. There's your kind of statistical significance. But if I measure just qubit 1, nothing's happened to it. So it stays in its base state. We haven't put it into superposition. It's as if it's a normal bit. However, if I entangle the states with that, this is another operator, it entangles it. It basically means whatever the outcome of this top qubit is, the bottom one will be the opposite. If I now measure that qubit, it goes to 50-50. But it should, okay, this might not be the opposite one. I think I couldn't get the opposite one to work. So it will be the same, sorry. So now what I've done though, is I've made a quantum circuit, 2 qubits, where I measure the qubit that I'm doing pretty much nothing to, but it's entangled to the one that's changing, and it does the same thing. And that's an example of ways you can construct it. The same way you can construct a coin flipping algorithm using different random functions or different logic. Same thing as that. So yeah, that's it.